This is registration number 260, presenting the project titled EAF Waste Heat Recovery for Steel Industry. In this video, I will walk you through the problem, our simulation approach, key results, and economic findings. For the introduction part, electric arc furnaces discharge flue gas at temperature up to 1200 degrees Celsius. This represents approximately 30% of total energy input being lost as waste heat. The global steel industry contributes around 7% of worldwide CO2 emission, making waste heat recovery a critical and urgent decarbonization strategy. Our project directly addresses this by designing a system that captures this wasted energy to generate electricity and preheat combustion air with zero additional fuel input. For the methodology part, I will show you the main flow sheet. Here is our complete 10 block flow sheet simulated in Aspen Plus version 15. Flue gas enters at 1200 degrees Celsius and 72,000 kilograms per hour. It first passes through B cool 1, cooling to 1000 degrees, then through B cool 2 down to 327 degrees Celsius, and B steam G then cools it further to 250 degrees Celsius. Notice this dashed line here. This is our QSG SW heat stream. It thermodynamically couples B steam G with B steam W, ensuring the heat extracted from the flue gas is explicitly transferred to steam generation. This makes our simulation thermodynamically correct. B steam W generates steam, which is superheated in B2 to 350 degrees Celsius at 12 bar. The mixer B3 mix handles the water feed. This superheated steam drives B turbine, our turbine. After expansion, steam is condensed in B cont and B pump recirculates the water, completing the closed Rankine cycle. Separately, B air preheater and B air heater preheat combustion air from 25 to 350 degrees Celsius. Two design specification automate conversions. DS steam fixes the flue gas exit at 250 degrees and DS air targets 350 degrees hot air temperature. The property method uses PENGROB with mixed solid, stream class and 7 components CO, CO2, N2, H2O, H2, O2 and SO2. For the simulation result, this is our stream summary. Here are the verified stream results from the final simulation. Flue gas enters at 1200 degrees Celsius and gas 800 exit as B cool 1 at 1000 degrees Celsius. The final flue gas exhaust exit at exactly 200 degrees Celsius. This way our design target and it has been met. On the Rankine side, B10, our steam result is fully superheated at 350 degrees Celsius and 12 bar before entering the turbine. Hot air confirmed 350 degrees. Our air preheating target is also met. Now for the APA equipment and the energy savings part. The Aspen Process Economic Analyzer sized all our equipment, heat exchangers, pump and turbine. The total installed capital cost confirmed by APA is $2,123,000 US. For the economic results TEA Excel sheet, we have this assumptions we made, and the annual electricity revenue from the turbine is approximately $889,000 US. Annual operating costs around $110,000 US. This gives us a net annual benefit of $779,000 and a simple payback period of 2.7 years. For the sensitivity analysis, our sensitivity analysis confirmed that even with a 30% reduction in electricity price or a 30% increase in capex, the payback period remains well under 5 years. For the cash flow part, the net present value over 20 years at the 10% discount rate is approximately $3.9 million US. The internal rate of return is 39.3% CO2 emission avoided are approximately 6,900 tons per year, with an additional carbon credit value of around $103,000 per year. Now for the conclusion part, to summarize, this project demonstrates that EAF waste heat recovery is both technically feasible and economically highly attractive. Aspen Plus B15 confirmed full system conversions, flue gas cooled from 1200 to 200 degrees, superheated steam at 350 degrees, driving the Rankine cycle, and all design specification converged. APA validated capital cost at $2.12 million, a payback period of 2.7 years, and an IRR of 39.3% make this an excellent industrial investment. The QSG-SW heat stream ensures thermodynamic correctness by explicitly coupling flue gas cooling to steam generation. a key engineering contribution of this simulation. Future work includes an AI surrogate model for deeper sensitivity analysis, full heat-axe block implementation, and a scale-up feasibility study. Thank you for watching. This was registration number 260, EF Waste Heat Recovery for Steel Industry. Thank you.